We have, over the last few days, taken a look at two equations that describe for us the mathematics of curved mirrors. Those two equations are, number one, the mirror equation, 1 over f is equal to 1 over dO plus 1 over di. And then we had, of course, the magnification equation, which is hi over ho equals negative di over do. Don't forget that negative. It's a pretty common mistake, actually, is to forget to write down that negative, even though it's written for us on our data sheet. F stands for the focal length, do is the object distance, di is the image distance, hi is the image height, ho is the object height. Can you tell me what units I should use for each of these? Focal length, do, image distance, and so on. What units should I use for those? Yep. Yeah, it doesn't really matter what units I use for any of those distances, as long as they measure distance, and as long as they're the same units throughout. The typical unit that we use for these is actually centimeters, because we're generally dealing with questions involving distances of centimeters, and it probably makes sense not to bother converting from centimeters when we've got all our distances already given to us in those units. Let's take a look at positives and negatives. That's the tricky part about this. The really challenging thing is to remember when something should be positive, when something should be negative. All of these variables kind of go together, f, do, and di. They're all positive and negative under similar circumstances. M, hi, and ho kind of go together as well. They're all positive or negative based on similar circumstances. Can you tell me what that similar circumstance is for the first category here, f, do, and di? What's the one word that I'm looking for here? Right, real or virtual. All of these things are positive or negative based on real or virtual. So in other words, the focal length is a positive number if it's a real focal point. Di is a positive number if the image is real. Do is a negative number if the object is virtual, and so on and so on and so on. When do we have a positive focal length? Okay, we have a real focal length, right? But when do we have a real focal point? Yep, Cassie? Right. If we have a concave or a converging mirror, then it's a real focal point. Therefore, we're going to make it a positive f. If it's a diverging mirror, or if it's a convex mirror, then we're going to make it a negative focal point. What about do? When is that positive for us? One word, if we're talking about just physics 30. Do is positive. Always. Do is negative, never negative. Because we never have a virtual object. Okay, it is possible to have a virtual object, but not in physics 30. So for us, it's always going to be a positive value. Di is positive when we have a real image and negative when we have a virtual image, and that depends upon the scenario. Okay, we can't just use a nice simple rule like convex mirror, concave mirror, positive, negative. It's not as simple as it is for focal length. What about hi, ho? When are they positive or negative? It's not based on whether it's real or virtual. Rather, it's based on whether they're upright or inverted. If the image is right side up, we should make it positive. If it's upside down, we should make it negative, and so on. M, the magnification, doesn't quite fall with the other two, but it's close. Hi and ho are always positive if they're right side up. A positive M almost always means that the image is right side up. But it can mean that the image is upside down if the object and the image are both upside down. Then M would be a positive value. So we kind of group it together with hi and ho. Doesn't quite fit, but 99 times out of 100, it still works. Okay, that rationale still works. Make sense? All right, let's take a look at the homework questions that we add on this stuff now on page 665. Number 4 to 8 and number 11. Any issues with any of those questions? 4 to 8 and number 11. Cool? Okay, 6. Is that it? 7? I was thinking about going over number 11. You want to do that? 8? Is that good? Yep. pretty much all of them then, right? 4, 6, 7, 8, and 11. 4 says compare virtual images with real images. What's the answer we're looking for there? Compare virtual images with real images. Right. One can be projected onto a screen, one can't. Which one can be projected onto a screen? It's the real image, right? The virtual image has to be, you physically have to look into the mirror to see it. Now, for a real image, it doesn't mean you can't look into the mirror to see it. It's just you don't have to. You can project it onto a screen. What does it mean by projecting onto a screen? Literally, what you see right now coming from this projector hanging from the ceiling, the image is being projected onto the board. Okay, that's an image that's being projected onto a screen. If, on the other hand, I had to physically get up on a desk and look in there, although I'm not going to do that because it's going to blind me if I do that, but if I had to look into there in order to see the image by looking into the lens, then that would be a virtual image. Well, this is you're going to see here tomorrow, actually, we're going to talk about the similarities between curved mirrors and curved lenses. Same basic principles apply, other than lenses allow refraction to take place, the bending of light, versus reflection to take place. But in the end, some lenses, depending upon the scenario, can produce a real image, an image that's projected onto a screen. Same thing with mirrors. Some mirrors can produce an image that's projected onto a screen, some can't. Okay, look into a mirror in the bathroom, it's a plain flat mirror, you can't project that image onto a screen. You've got to look into the mirror to see it. But if you have a curved mirror, a concave mirror specifically, then sometimes you can project it onto a screen, just like I'm projecting that image right now from the projector onto a screen through that lens. Okay. 6, describe the path of the 3 rays that can be used to determine the characteristics of an image formed in a curved mirror. Describe the path of those 3 rays. How about we describe them as we draw them here? Doesn't matter where we put our object. Okay, the rays that we can draw are going to be the same. Let's put our object out here. The first ray, we know this, right? The first ray is parallel to the principal axis, down through the focal point. The second ray is down through the focal point, parallel to the principal axis. Where's the third ray go? Down through the center, back up through the center. Where do they intersect with each other? We should have found, if we do this perfectly, that they'd intersect all in the same spot. It's close. They intersect with each other right here, meaning that's the top of my image. It's going to look like this. So describe the path of those 3 rays. First ray, parallel then through the focal point. Second ray, through the focal point, then parallel. Third one goes down through the center of curvature and then back up through the center of curvature. Number 7. What does a diverging convex mirror have a virtual focal point and not a real focal point? Here's concave. Here's convex. What happens to a ray of light striking this concave mirror? Where does it go? Through the focal point. Where does this one go? Through the focal point. Rays really converge at the focal point. What happens to the next one? Where does this one go? Up, away from the focal point. Where does this one go? Down, away from the focal point. These ones don't really converge at the focal point. They virtually converge at the focal point. In other words, they diverge away from the focal point. So the question again said, why does a diverging convex mirror produce a virtual focal point, not a real focal point? Because the rays don't really converge there. They diverge away from the focal point, which is like they're converging there. They're virtually converging there. Okay? Yeah. Yes. Mm-hmm. Yep, that's exactly it. Yep. When you look into the mirror in the bathroom, you perceive the image to actually be behind the mirror. Sometimes, I don't know if you guys have ever experienced this, but sometimes you walk into a room that's got a lot of mirrors on the wall. Like it's a ballroom or a banquet room or something. It's got mirrors on one side of the wall. And you walk in, and your initial perception, before you have a chance to really think and observe and whatever, but your initial perception is, this room is huge. It appears to be sometimes twice as big as it is. You ever notice that? Okay. you, when you look into that mirror, are seeing a virtual image of the rest of the room. That virtual image actually appears behind the mirror. Okay, so in other words, what's happening in your eyes, your brain, actually more than your eyes, your brain is interpreting the rays of light that are reflecting off of the mirror as if they kept going through the mirror. The dotted lines kept going through the mirror. And that's where I end up seeing the image. Okay, does that make sense? I'm not sure if my sub yesterday in the podcast that he was showing got as far as the fish in the water. Did he show you that one? And how the fish appeared to be in a different place? Right? It's because our brains think that the light always went in a straight line. Right? Really, it bent when it hit the boundary between the water and the air. But our brains don't perceive that. Our brains see it as having gone in a straight line. That's why the fish appeared to be in a different place than it really was. Yep. I thought it was a good fish. If you don't like it, draw your own fish. There. Take that. I thought it was a good fish. Worked on it for a long time, too, and now it's having people making fun of me. Was he? Good, good. Excellent. Let's take a look at number 4 here now. An object 4 centimeters high is located 10 centimeters from front of a concave mirror. A concave mirror tells us that our focal point is positive because it's converging. We have an object distance of 10 centimeters. We have an object height, HO, we're going to make it 4 centimeters. We have a virtual image that's produced, and it's 5 centimeters high. That's going to be DI. That virtual image is going to be positive 5.0 centimeters. Positive because it says it's an upright or an erect image. 5.0 centimeters. Sorry, that's HI. Yes, yes, thank you. HI. And we want to find the focal length of this mirror. But we only have one equation that allows us to find focal length. It's my mirror equation, 1 over DO plus 1 over DI. But unfortunately, we don't know what DI is here, so we got to find that. Let's say M is equal to HI over HO equals negative DI over DO. We're allowed to use M is equal to HI over HO, or M is equal to negative DI over DO, or the combination of the last two parts, HI over HO, negative DI over DO. 5 over 4 equals negative DI over 10. DI is going to work out to be 12.5, right? Negative 12.5 centimeters. Now we can plug it back into the main equation that we have. Oh, that's a negative 12.5, isn't it? How do we do that on our calculators? Seems a little bit ugly. I don't know about you guys, but I wouldn't be a big fan of trying to find a common denominator for 10 and negative 12.5. It wouldn't be crazy hard, but the easiest way to do it, 10 x to the minus 1, subtract 12.5 x to the minus 1. 1 over 10 minus 1 over 12.5, isn't that the same thing as saying 1 over 10 plus 1 over negative 12.5? Yeah, it's exactly the same thing, so that works. 0.02, is that my answer? No, what do we got to do with that? X to the minus 1, flip it over. We're going to find that F is equal to 50 here. And it's a positive value. Got it? I'll tell you a way that we can often check this and see if we're in the right ballpark. Draw a ray diagram. Okay, if you draw the ray diagram for this, now we've got a focal length of 50 centimeters, and we're placing it 10 centimeters in front of a concave mirror. Draw the ray diagram and see what you get for the image. See if you get something that approximates what the numbers are in the rest of that question. In this case, I think you would. Finally, number 11 says some flashlights and headlights use a concave mirror to help generate light, a light beam. If the light source is positioned at the focal point of the mirror, would all of the reflected rays travel outward parallel to the principal axis? Yes or no? Here's my concave mirror. Here's my focal point where I'm putting my light. We've got a whole bunch of rays of light reflecting or coming from that light source here. Are they all going to reflect off of the mirror parallel to the principal axis? The answer is, Michael, yes. If this ray of light came this way and reflected off of the mirror, it would go to the focal point. So if it's going the other way, why wouldn't it go parallel to the principal axis? All rays parallel go through the focal point. All rays from the focal point go parallel to the principal axis. That's why your headlights in your car aim more or less ahead of you and not in every which direction. The light is directed straight ahead of you. That makes sense? Now, you always do see a little bit of light coming out here, right? Coming out here from your headlights. Well, there's a couple reasons for that. Number one, the mirror that's behind the light isn't necessarily perfect, so it's not necessarily going to direct the light perfectly in a straight line. The other thing is, there's also not light just coming backwards toward the mirror. There's light going in every which direction forwards from that light source as well, right? It's just not focused in one line like the light that comes off of the mirror is. How many people got that answer? Got that answer correct, that is. Good. Good there? Yesterday, you saw a podcast from last year that explained to you what the concept of refraction means. Refraction is the bending of light. And the bending of light happens because something else happens first. When light goes from one medium to the other, it will change speeds. If light goes from air to water, it will slow down from about 3 times 10 to the 8 meters per second to somewhere in the range of 2.3 times 10 to the 8 meters per second. If light goes from air to glass, it will slow down to about 2 times 10 to the 8 meters per second. If light goes from air to diamond, it will slow down to about 1.3 times 10 to the 8 meters per second. Light changes speed when it goes from one medium to the other. Now, as a result of that light changing speed, 2 other things change as well. Number one, the wavelength. You guys saw in the analogy yesterday with the soldiers walking across the parking lot into the swamp. You guys saw that because the speed changed when the soldiers marched in the swamp, the wavelength changed. Those wave fronts got closer together when the speed changed. When the speed changes because of a change in medium, the wavelength changes. But what else also changes? And this is probably the most important part of it. The direction. Right? When the speed of the wave decreases, then the wavelength will also decrease, but the angle will also decrease. Now, one variable stays the same. Which one is that? Which one is it? Frequency, right. The wavelength will change as a result of the speed changing. The direction will change as a result of the speed changing. The frequency, once a wave has been made, always stays the same. The index of refraction is simply a number that represents a measure of how much light will bend when it goes from one medium to the other. How much light bends when it goes from medium A to medium B. Now, what do you think it's dependent upon? Why does light bend? Why did the path of the soldiers change? Why did the path of the soldiers bend when we went from one medium to the other? Fundamentally, the direction changed, the wavelength changed, all because, but let's do it in terms of the wave, not the medium. And therefore they moved slower, right. The wavelength changed, the direction changed because the speed changed. So if we're giving you a number here that represents how much light bends when it goes from one medium to the other, it's going to be dependent on the speed, right? Because that's what causes light to bend, is a change in speed. If it's dependent upon the speed, then we're going to write down a little equation to describe this as such. N is equal to C over V. C is the speed of light in a vacuum. It's always going to be 3.00 times 10 to the 8 meters per second. V is the speed of light in whichever medium we're trying to find the index of refraction for. For glass, we're going to say the speed is about 2.00 times 10 to the 8 meters per second. For cubic zirconium, you ever heard of cubic zirconium? Girls have heard of cubic zirconium because they're kind of on the lookout for that, right? When they get older, it's like, I don't want some guy to give me a cubic zirconium ring. Guys have heard of cubic zirconium because they're like, yeah, I'm going to try this one. Let's see if this will work. It's a lot cheaper. Cubic zirconium is like fake diamond, okay? In cubic zirconium, I don't know why I picked that one to give you right now, but cubic zirconium, the light slows down to about 1.5 times 10 to the 8 meters per second. Can you tell me which one is going to have the higher index of refraction, glass or cubic zirconium? Yeah, cubic zirconium will have the higher index of refraction. And that's why cubic zirconium, although not as good as diamond and not as valuable as diamond, is better than glass because it has a higher index of refraction because it causes light to slow down more. The implications of that we're going to see a little bit later here today. Glass, the index of refraction would be about 1.5. Cubic zirconium, it would be about 2. The smallest possible number for the index of refraction would be what number? 1. You can't get a speed that's bigger than 3 times 10 to the 8. In order to get a number for n that's smaller, you have to have a number that's bigger than 3 times 10 to the 8. Can't happen. Smallest number you can have, biggest number I should say on the bottom, you can have is 3 times 10 to the 8, giving us the smallest n of 1.00. We would have an index of refraction of air if it was 1.00, or a vacuum, 1.00. Everything else causes light to slow down more, causes a bigger index of refraction. Which one bends light more, glass or cubic zirconium? Glass has a lower index of refraction, but which one bends light more? Cubic zirconium, because it has a bigger index of refraction, because it has a bigger change in wavelength. A smaller change in wavelength, because it has a bigger change in wavelength and a bigger change in speed. Okay. You also heard yesterday about this phenomenon called dispersion. Dispersion is the process whereby light breaks up when it goes into a triangle, a prism of some type. Why does that happen? Well, white light consists of all the different colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. And when that white light strikes the boundary between the air and the prism, it'll bend. But the prism, whether it's made out of glass or plastic, has a slightly different index of refraction for every different color. That means the index of refraction for red is slightly different than the index of refraction for violet. That means when the white light, which consists of all the colors, strikes the boundary, each different color will bend a slightly different amount. Tell me, look at the diagram here. Tell me which color produces the highest index of refraction for this material. Can it be red or violet? Violet, right? Violet bends more. It has to have a higher index of refraction. Okay, which one produces a bigger change in speed? In other words, which color of light slows down the most when it goes from air to glass? Yeah, it's going to be violet again. The bigger the index of refraction, the bigger the change in speed. The bigger the difference between the pavement, yesterday's analogy, right? The pavement and the swamp, the bigger the difference between those two, the more the soldiers slow down, the bigger the index of refraction, we'd say. All right, which one has the biggest change in wavelength? Violet. Which one slows down? Which one slows down the least? Which one would it be? Red light, right? I think I mentioned in the podcast yesterday about a couple places that I've seen this, really good examples of this myself. You guys have seen it a million times too, right? But some examples are better than others. Ironically, when you actually try to do it with a real prism, it's hard to make it work. And when you see it by accident, it tends to work better than see it by accident. I think I mentioned in the podcast yesterday, if you walk out past the cafeteria at a certain time of day, depends on where the sun is, right? It has to be a bright sunny day as well. The light from the sun goes through one of those little triangular display cabinets right in front of the cafeteria. And if you go through right at the right time of day, The light strikes it at just the right angle where you can see this rainbow on the floor. Red, orange, yellow, green, blue. Have you seen that? Yeah. It's good. It's a good example of it, too. It works really well. The other place I've seen it, probably the best example, and I think I mentioned this yesterday as well, was at a friend's house in a fish tank. Literally, the sun is coming through the front window, going through this fish tank, and producing this beautiful spectrum of red, orange, yellow, green, blue, indigo, and violet on the white wall that's behind it. Okay, perfect example of it. Where else have you seen it? Where else have you guys seen it? Besides maybe the atrium or fish tank or whatever. Rainbows. And this is exactly what happens with rainbows. Light splits up. White light coming from the sun splits up. What causes it to split up? Well, it's not prisms. It's rain droplets. Right? Little droplets of moisture that act as the prism. This table, obviously you don't have to memorize this table. It just gives us different indices of refraction for different materials. You can see that air and a vacuum are pretty much the same because the speed of light in both of those is pretty much the same. We're going to make them both the same. Let's call them just both 1.00. Tell me which material that's listed up here causes light to slow down the most. Air? Actually, let's not count air or vacuum. Which one causes light to slow down the most? Ice or diamond? Diamond, right? Because it has the biggest index of refraction, the biggest change in speed. Which one causes the smallest change in wavelength? What is it? Ice causes the smallest change in wavelength. Which one causes the smallest change in speed? Ice. The smaller the index of refraction, the smaller the change in speed, the smaller the change in wavelength, and the smaller the change in direction. Okay. Finally, this equation that was known as Snell's law that you learned yesterday, sine theta 1 over sine theta 2 equals v1 over v2 equals lambda 1 over lambda 2 equals, circle this in red because a lot of people mess up on that. You get in that habit of writing 1 over 2. Well, the index of refraction is 2 over 1. Because as v gets bigger, as v goes bigger, we're going from a high to a low index of refraction. They're inversely related. Lambda 1, v1, theta 1, n2. Lambda 2, v2, theta 2, n1. All right, you had some questions on this as well yesterday. Page 668 was the first set, and page 670 was the second set. Any of those questions on page 668 that we need gone over? No? Any of those questions on page 670 that we need gone over? My class this morning had a little bit of trouble with a couple questions on 670 because, question number 2 particularly, because it doesn't tell us what medium 1 is. It says, right where the wavelength of 737 enters quartz glass, but we didn't know what N1 was. Lambda 1, 737. Theta 1, 25 degrees. What's N1? We're going to assume in this case that it's air. N1 is 1.00. So it's going from air to quartz glass. N2 quartz glass, I think, was 1.47, isn't it? We're looking for the angle of refraction, theta 2. We're looking for lambda 2. I'm going to say lambda 1 over lambda 2 equals N2 over N1. I always like it when this happens. You get 1.00 on the bottom. Makes the division a lot easier, right? You're dividing by 1. Lambda 2 goes up by multiplying. 1.47 goes down by dividing. We get 737 over 1.47. Hey, by the way, is it okay that I didn't convert that to meters? Yeah, the units cancel, right? So it is okay that I didn't convert it to meters there. Lambda 2 equals 501 nanometers. We do almost the same thing for theta 2, except that the math is a little bit trickier because we have to do an inverse sine thing. Okay, let's take the n1 up by multiple. n1 is equal to 1, right? So we can get rid of that. Sine theta 2 ends up being equal to sine theta 1 over n2. Take the inverse sine of that. Looks kind of ugly here, but it's not really that bad if you do it in steps. Get a number for sine theta 1, divide it by n2, take the inverse sine of that. The angle we should get is 16.7 degrees. Is that okay? This is where we left off yesterday on the podcast. Total internal reflection. It's a phenomenon. I'm glad you wrote the notes down yesterday because I have a tough time spelling phenomenon. I don't really want to write it down again. Total internal reflection is a phenomenon whereby light doesn't refract when it goes into a new medium, but rather it reflects. But it doesn't do that all the time. It only does that some of the time. When you throw a rock just straight down into the water, it changes speeds as it goes into the water from the air, but it still goes into the water. It slows down, but it still goes into the water. When I throw a rock at a bit of an angle now, as measured from the vertical, almost straight down, but still at a bit of an angle, then the rock will still go into the water, but it will change speed, and its direction will also change as a result of that change in speed. Effectively, it's refracting. If I throw a rock at a bigger angle, it still, again, goes into the water, but decreases speed and therefore changes direction as well. If I increase the angle of incidence, though, to a great enough point there, now, like this, throwing it almost along the surface of the water, then my angle of incidence is really, really big right now, and I may have exceeded a minimum angle necessary to cause the rock to skip along the surface. We call that the critical angle. Now, light does almost the same thing. If I shine light on a boundary between two materials, I can cause, if I increase the angle of incidence to a great enough degree, I can cause that light to reflect. That's called total internal reflection. But the analogy kind of falls apart a little bit because it works when you're going from air to water. You're throwing that rock from air to water, bounces off. Total internal reflection with light only happens the other way around, when you're going from a high index of refraction to a low index of refraction. Won't happen when you're going from low to high. Here's why. Here's my boundary between the two materials. This is going to be air. This is going to be water. Low index, high index of refraction. Here's my ray of light. We're going to call this theta 1. As it goes into the new medium, what's going to happen to it? Speed up or slow down? If it slows down, the wavelength is going to decrease as well, and the angle is going to decrease as well. In other words, theta 2 is going to be smaller than theta 1. It's increased my angle of incidence quite a bit. Theta 1 is now a much bigger number. Theta 2 is going to be bigger than it was in the last example, but it's still going to be smaller than theta 1 is. Theta 2 will never be bigger than theta 1. Therefore, theta 2 will never be such that this ray of light will reflect. If, however, I go the other way around, let's say from glass to air, where we have a high index of refraction to a low index of refraction, something else is going to happen. First ray of light, theta 1, because it speeds up, it bends away from the normal line. Theta 2 is bigger than theta 1. Once again, theta 2 is bigger than theta 1. If I increase my angle of incidence enough, then theta 2 is going to becomes 88, 89, and 90 degrees. That's when total internal reflection begins to occur. That's when it no longer refracts. That's when theta 1 change its name to theta c. my critical angle, the angle at which total internal reflection begins to occur. What happens if I increase it even more? What happens if theta 1 becomes even bigger? Now it bounces off. Now we don't have to do Snell's law, right? It's just theta 1 equals theta 2. Angle of incidence equals the angle of reflection. All right? And we went through this yesterday with my well-drawn fish. I think it was red, wasn't it? That one's slightly better. Yeah. What? I put an eye on it. I put a smiley face on the last one? All right. Let's do that then. Oh, that's right. He had a smiley face because he wasn't being caught, right? So millions of rays of light reflect off of this fish in every which direction, but we only care about one of these rays of light that reflects off of the fish. It's this one that we care about. When this ray of light strikes the boundary between the water and the air at an angle that we call theta 1, it's going to refract. It's going to go into the second medium, air, and it's going to bend. It's going to bend because the speed's going to change. Is it going to speed up or is it going to slow down? It's going to speed up. We're going from a high index of refraction to a low index of refraction. It's going to speed up. Because it speeds up, the wavelength is going to increase, but the angle is going to increase as well. In other words, we're going to say here that theta 2, the angle of refraction, is greater than theta 1. What happens, though, if I back up? What happens if me, the guy that's standing on the side of this pond, I back up to here? This ray of light that did refract into my eyes no longer refracts into my eyes. I can't see it. But the good news is there's a few million other rays of light that might refract into my eyes. Let's pick another one. Let's pick this ray of light now. This ray of light, let's go red here. This ray of light goes up here, strikes the boundary between the air and the water right here. Theta 1 is now bigger than it was before, right? We've increased the angle of incidence. When it goes into the air, the angle of refraction is going to be greater as well. It's speeding up. We're going to increase the angle of refraction, theta 2, so that it's bigger than theta 1 and bigger than the other theta 2 was. The problem is this. Because we're going from high to low index of refraction, we may very well have exceeded right now what we call the critical angle, the angle at which total internal reflection begins to occur. So this ray of light that would refract into my eyes here maybe doesn't. Maybe it reflects instead, because maybe theta 1 is too big. What do I see there now? Nothing. Because although the rays of light coming out of the pond, coming off of this fish out of the pond, and if you're a giant, so that your head is up here, you can see it. If you're not in line of one of those rays of light that come out, you don't see anything. You ever notice that before? Sometimes, you're at the edge of the pond, you can see the bottom of the pond. But if you back up, you can't see the bottom of the pond anymore. You hit the golf ball in the water, you're approaching it, you can't see it. All of a sudden, when you're standing right on top of the pond almost, you can see the golf ball. Now, it's not where you think it's going to be. Okay? It's somewhere else, but at least you can see it because you're close up, and the ray of light that's reflecting off of it that comes into your eyes isn't reflecting off of the boundary. By the way, where would we see the fish in the first case? Yeah, let's say I'm standing back here near the edge of the pond again. Where would we see this fish? We talked about this earlier, right? Our brain thinks that this light has always traveled in a straight line. So the fish is going to appear to be right there. Appears to be close to the surface, right? What else appears to be close to the surface? Bottom of the pond, right? Because the bottom of the pond is reflecting light the same way as the fish is. So it appears as if the pond isn't nearly as deep as it really is. You ever notice that? When you're standing beside a pond or a pool or something, you ever notice that it's actually deeper when you jump in than it appears to be when you're standing by the side? Yeah. Yeah. Where would you have to be to see this red ray? You'd have to be in the pond. You'd have to be laying down on the side of this pond right there. But where would it appear to be to you? The fish would appear to be in the sky, but having said that, what else would appear to be in the sky? The water as well. The bottom of the pond and the water as well. So although it would appear to be up relative to where you are, it wouldn't appear to be a fish flying through the air. It would appear to be still a fish swimming through the water. It would just be above you instead of below you, that's all. Well, that's a good question. If the ray of light is this ray of light is reflecting off of the top of the fish, then what you'd see right here would be the top of the fish. So the fish would effectively be upside down. Yeah. Go ahead. Absolutely it could. Absolutely it could, yeah. Sorry, would it actually happen? Yes. Absolutely would happen. I'm sorry? If you're at the right angle, yeah. Yeah. Here is a much more important application of total internal reflection. What's that? About half of you are someday probably going to receive one of these, and about half of you are someday going to probably give one of these. Now, I'm going to give you a little piece of advice for both of you, the half that's going to receive and the half that's going to give one of these. When I bought the engagement ring for my wife 15 years ago, I went to a place called Spence Diamonds. You guys have heard those commercials on the radio, right? Sean, he sold me the diamond. He was the guy. He was the guy that sold me my diamond. Yeah. He did a good job, actually. He was very good, actually. He was. When I went in there, I had no idea what I was looking for. I go in there and I'm looking around, and this guy, Sean, comes over and starts talking to me and starts saying, you can pick rings you like, and they have in their showroom they have these replicas of the rings with glass in them, so you kind of know what they look like. They don't shine as much as diamonds, but you kind of get a pretty good idea what they look like. And the benefit of that is you can pick them up. They don't have to worry about people stealing them, right? Because they're fake rings, right? Nobody really wants the fake ring. So what you do is you pick out the ring that you like, and then you go sit in his office and you talk to him about a diamond, like what size of diamond you should get, and so on, and how much you want to spend on it, and so on and so on. Anyways, he explains to me that there's when you're buying a diamond, there's 4 C's that are important. First one is, well, no particular order, the clarity of the diamond. Obviously, the more clear the diamond is, the better. If it's kind of foggy, then that's not so good, right? We don't want, foggy diamonds. Another one is the color. Okay? The color is important. Usually, you don't want any color, but he said if you have a diamond that's actually got a lot of color in it, then that can be good because it's rare and it can be valuable because it's got a lot. So usually, you don't want any color. So you want it clear and you want no color. The third one is the carats, the size of the diamond. Obviously, the bigger the diamond, the more you pay for, right? The fourth one is the cut. And he explained to me that that's the most important one, the cut of the diamond, because the cut is what makes it sparkle. So he goes through this explanation to me as to why the cut mattered so much and how they do it so that the cut is just right. And then afterwards, it's funny actually, afterwards, it didn't occur to him to ask me what I did for a living before he did this. Afterwards, he says, so what do you do for a living, by the way? And I told him that I was a physics teacher. And the look on his face was actually kind of priceless at the time. Because it was kind of that look of oh, I hope I passed. but he did. He did a really good job. And his explanation was perfect as far as physics goes. It was no, terrible marketing stuff in there at all. It was all good physics. Anyways, here's what happens. Light comes from every which direction into this diamond, but primarily it comes from above, right? You don't get very much light. You got a diamond ring on. You don't have very much light coming from below, going through the diamond, or coming from the side. Primarily, that light is coming from above. By the way, all diamonds are cut like this, exactly like this. Now, they may be square on the top, or they may be oval on the top, or rectangle on the top, or circular on the top, but a cross section, a well-cut diamond always looks like this, always. Okay, if it doesn't, then you shouldn't buy it. The shape on the top doesn't matter. The shape on the side, okay, as a cross section, absolutely matters. The rays of light come down from the sky or from the light bulb or whatever. Okay, as they go, let's assume that they go straight in there. They're going to slow down dramatically when they go into that diamond, but they're not going to change direction because they're going straight in there. What happens when they hit this boundary over here? Well, there's a certain angle there that we call theta 1. If theta 1 is smaller than the critical angle, then this ray of light is going to refract out here such that theta 2 is bigger than theta 1. But if theta 1 is bigger than the critical angle, then what's going to happen to that? It's going to reflect. That's the sparkle. That's the first sparkle that you see, is that reflection of light off of the inside surface of the diamond. Now, we don't see sparkles when light doesn't reflect off of things, right? Okay, we see sparkles when light reflects off of something shiny. Okay, when it reflects off of the inside of a diamond. So there I've got a sparkle. Now what happens? It goes to the other side. There's an angle of incidence right there as well. We'll call that theta 1 now. What happens? Well, if theta 1 is smaller than the critical angle, then the ray of light is going to refract up here. That may be what happens in cubic zirconium. Okay, you might get one reflection taking place. Cubic zirconium has a pretty high index of refraction, but it's not as high as diamond. Because it's not as high as diamond, the critical angle is bigger. That means it requires a bigger angle in order to reflect. Diamond has such a high index of refraction, it has a low critical angle. Probably one of the smallest critical angles that you can have. Therefore, you get more light reflecting off of the inside surface. It's not nearly as hard to exceed that critical angle when you have a small critical angle. Now, if it's cut wrong, if it's, let's say it's glass or it's cubic zirconium, maybe you get one sparkle, and then on the other side, it goes out the side. If it's cut wrong, then again, maybe you get one sparkle, but it reflects off at an angle such that it just goes out the other side. Okay, if it's cut perfectly like this, then you're going to get, for each ray of light, one sparkle and another sparkle. That make sense? So girls, if it doesn't sparkle, don't accept it. Because he's either cheap or didn't listen in his high school physics 30 class, one of the two. Anyways, you shouldn't marry him in either case. Guys, if it doesn't sparkle, don't buy it, because it's not real. Either it's not real, it's not diamond, or it's cut poorly, in which case it's not very valuable. Yep. Well, you get it fitted into a ring, but if you ever notice the side of a diamond ring, it's not encased. No, not at all. There's these little arms. There's usually probably 4 little arms with little hooks, little claws almost, that keep it in. You can actually see the diamond from the side as well. But even if it was completely encased, it doesn't really matter, as long as it's not encased in the top. Okay? You can have a piece of metal right there and a piece of metal right there. It doesn't matter. It's reflecting off of the inside surface of the diamond, so that doesn't really matter. Now, there's an argument maybe that, look, if you got a really, really shiny piece of metal, then maybe it doesn't need to reflect. Maybe it goes through the diamond and then reflects off of the piece of metal as opposed to the diamond itself. But inevitably, that's going to be an imperfect reflection, and therefore, reflecting in the wrong spot, it's not going to sparkle as much. Plus, it's nice of a diamond ring when you've got your diamond pretty much all covered up by a piece of metal, right? Make sense? Well, how do we know when the critical angle is exceed it? How do we know what the critical angle is? And we do a picture going from a high index of refraction to a low index of refraction, because this only happens when you're going from high to low. Increase my angle of incidence to a great enough degree that it goes along the surface there. Total internal reflection begins to occur. In other words, the critical angle is when theta 2 equals what? 90 degrees. So we're going to use Snell's law. Sine theta 1 over sine theta 2 equals v1 over v2 equals lambda 1 over lambda 2 equals n2 over n1. But when we're trying to find theta c, the critical angle, the angle of incidence at which reflection begins to occur, we're going to always set theta 2 equal to 90. And then whenever we exceed that critical angle, we don't need to do any math because we know that it reflects already. It's a critical angle for a quartz glass air interface. Quartz glass had an index of refraction of 1.47. Air was 1.00. Which way am I going? It doesn't say whether I'm going from glass to air or air to glass, right? Do we know which way we're going here, Ronnie? How do you know that? Refraction, yeah. Perfect. Okay, perfect. Reflection only occurs when you're going from high to low. Now, the other thing is, they probably would have said air glass if they meant going from air to glass, right? Okay, but even if they kind of mix that up a little bit, we're still okay because we know that it has to be going from high to low in order for this to take place. All right, so let's say sine theta 1 over sine theta 2 equals n2 over n1. Sine theta 1 becomes sine theta c, the critical angle, and sine theta 2 becomes sine 90. Right? The critical angle occurs when theta 2 is equal to 90 degrees. It's equal to n2 over n1. That's equal to 1.00 over 1.47. What's sine 90? It's 1. So it becomes sine theta c equals 1.00 over 1.47. Theta c is equal to the inverse sine of 1.00 over 1.47. What do we get there? Theta c equals 42, we're going to say 42.9 degrees. So if you have 42.8 degrees, then it's going to refract. It's going to go out the material out the other side. If you have 43.0 degrees, it's not going to refract, it's going to reflect, bounce off the inside surface. Okay? Yeah, 60 would bounce off as well. Anything above 42.9, and there's no upper limit to that, right? Anything above 42.9 as measured from the normal line gives you reflection taking place. Now, a quick question here. Quartz glass has an index of refraction of 1.47, causes reflection to occur at 42.9 degrees. Diamond has an index of refraction of 2.42. It causes reflection to occur at a much bigger or smaller angle? Smaller angle. So the bigger the index of refraction, the smaller the critical angle will be. Does that make sense? And that's why you get more light reflecting in diamond than you do in glass, because it has a smaller critical angle, and it's a lot easier to exceed the critical angle when it's a smaller value. So Jesper, when you go back to Finland, and your friends ask you what you learned in Canada, you say, I learned how to not get scammed on buying a diamond ring.
Yes.
You can buy a good quality diamond.
During my exchange.
The only thing you learn during the exchange.
Ever.
And that's right, and the best song ever. That's right.
I have watched the bad about English.
Okay. Good news. Only one question to do. 3 parts.